The Big Bang is the origin story of everything. Every atom in your body, every star in the sky, every galaxy spinning through the void, all of it traces back to one violent moment 13.8 billion years ago. But here's the problem nobody talks about. If the Big Bang created everything, then what created the Big Bang? This isn't just a philosophical riddle. It's a question that shatters our understanding of causality, time, and existence itself. Scientists have proposed answers that sound like science fiction. Some say the universe bootstrapped itself into existence. Others claim it emerged from nothing at all. A few suggest it was born from the death of an earlier universe. The truth is stranger than any of these proposals, and more disturbing, because the answer might reveal that the Big Bang wasn't the beginning. It might have been the middle, or there might be no beginning at all. Stay with me. We're about to dismantle everything you thought you knew about creation. Before time existed, the Big Bang didn't happen somewhere. It happened everywhere, all at once, in a space smaller than an atom. This is difficult to visualize because our brains evolved to understand objects existing in space and time. But at the moment of the Big Bang, there was no space, there was no time. Both came into existence simultaneously with matter and energy. This is not a metaphor. This is what the mathematics of general relativity tells us. Einstein's equations describe space-time as a dynamic fabric that curves in the presence of mass and energy. Run these equations backward in time, and the universe contracts. Galaxies that are now billions of light years apart converge. Stars that burned and died merge back into primordial gas. Eventually, everything collapses into a point of infinite density. This is called a singularity. At this point, the equations break down completely. Temperature, density, and curvature become infinite. The laws of physics, as we know them, cease to function. This singularity is often called the beginning. But that language is misleading. A beginning implies a moment in time when something started, but time itself emerged from the Big Bang. There was no before the Big Bang in the conventional sense, because before is a temporal concept and time didn't exist yet. Asking what happened before the Big Bang is like asking what's north of the North Pole. The question contains a category error. It applies a concept that only makes sense within a framework that didn't exist yet. Yet, our intuition rebels against this. Surely something must have caused the Big Bang. Every event we observe has a cause. Causality is fundamental to how we understand reality. Billiard balls collide because cues strike them. Stars form because gas clouds collapse under gravity. Effects follow causes in an unbroken chain extending backward through time. But at the Big Bang, this chain appears to terminate. The universe has a finite age. Trace causality backward far enough and you hit a wall. The wall is the singularity where causality itself breaks down. Some physicists argue the singularity isn't real. It's an artifact of taking general relativity too seriously in a regime where it shouldn't apply. General relativity is a classical theory. It treats space-time as smooth and continuous. But quantum mechanics tells us that at small enough scales, everything becomes discrete and probabilistic. At the Planck scale, around 10 - 35 meters and 10 - 43 seconds after the Big Bang, quantum effects dominated. Space-time itself was subject to quantum fluctuations. It wasn't smooth. It was foamy, chaotic, probabilistic. At these scales, the very concepts of space and time become fuzzy. You cannot specify an exact moment or location. The usual rules of cause and effect dissolve into quantum indeterminacy. This suggests the singularity is not a physical reality, but a mathematical artifact. It represents the limit where our current theories stop working. General relativity and quantum mechanics both break down at the Planck scale. We need a theory of quantum gravity to describe what really happened, and we don't have one yet. Several candidates exist. Loop quantum gravity suggests space-time is made of discrete units. String theory proposes fundamental strings vibrating in higher dimensions. Each theory handles the Big Bang differently, but none is confirmed. Without quantum gravity, we cannot definitively say what the universe was like at its earliest moments. The singularity might be real, or the universe might have bounced from a previous contracting phase, or it might have emerged from a quantum fluctuation, or something else entirely that we haven't imagined yet. What we can say with confidence is this. Approximately 13.8 billion years ago, the universe underwent a rapid expansion from an extremely hot, dense state. This expansion continues today. We observe it directly through the redshift of distant galaxies. We detect its afterglow in the cosmic microwave background radiation. The evidence for the Big Bang as an event is overwhelming, but evidence for what caused the Big Bang is absent. The beginning remains opaque. This opacity frustrates the scientific method. Science works by forming hypotheses, making predictions, and testing those predictions through observation. But we cannot observe the moment of creation directly. We see its consequences, the expansion, the background radiation, the abundance of light elements. But the cause remains hidden behind an information horizon. Light from the earliest moments has been stretched and diluted beyond recovery. The data we need is gone, scattered into entropy. Some propose that asking, what created the Big Bang, is meaningless. If time began with the Big Bang, then created implies a temporal sequence that doesn't apply. The Big Bang simply is. It's a brute fact about reality that requires no further explanation. This satisfied many people. It feels like giving up, like declaring a mystery insoluble rather than working to solve it. But it might be the correct answer. Not everything requires a deeper explanation. Some facts might be foundational. The Big Bang could be one such fact. Yet even if the Big Bang itself needs no cause, we can still ask why the universe has the particular properties it does. Why 3 dimensions of space? Why this particular set of physical constants? Why inflation, dark matter, dark energy? These questions don't ask what came before time. They ask why the universe emerging from the Big Bang took the form it did rather than some other form. These questions are scientifically tractable, and pursuing them reveals something unexpected about the nature of creation. The universe appears fine-tuned for complexity. Change any fundamental constant by a small amount, and stars don't form, atoms don't bond, or the universe collapses immediately. This fine-tuning demands explanation, and the explanations proposed lead directly to ideas about what, if anything, might have existed before the Big Bang, not in a temporal sense, but in an ontological sense, a deeper level of reality from which the Big Bang emerged. The quantum vacuum. The universe emerged from nothing. This statement sounds absurd. How can something come from nothing? Common sense says nothing means the absence of everything. No matter, no energy, no space, no time. True nothingness. But physics defines nothing differently. In quantum mechanics, the vacuum is not empty. It seethes with activity. The Heisenberg uncertainty principle states that you cannot simultaneously know both the position and momentum of a particle with perfect precision. There's always a fundamental uncertainty. This uncertainty extends to energy and time. Over short enough time intervals, energy can fluctuate wildly. Virtual particle-antiparticle pairs pop into existence, borrowing energy from the vacuum, then annihilate moments later, repaying the debt. This happens constantly, everywhere, even in the emptiest regions of space. We know virtual particles are real because they produce measurable effects. The Casimir effect demonstrates this directly. Place two uncharged metal plates very close together in a vacuum. Quantum fluctuations occur between the plates and outside them, but the narrow gap between plates restricts which wavelengths of virtual particles can form. More fluctuations occur outside than inside. This creates a pressure difference. The plates are pushed together by nothing but vacuum fluctuations. This has been measured. The effect is real. If vacuum fluctuations can push metal plates together, perhaps they can do more. Perhaps they can create universes. This is the idea behind the quantum creation hypothesis. The entire universe might be a quantum fluctuation, not a small one, not a particle-antiparticle pair, but space-time itself, fluctuating into existence from a quantum vacuum. Physicist Alexander Vilenkin proposed exactly this in the 1980s. He calculated that a small, closed universe could tunnel into existence via quantum mechanics. This process requires no prior matter or energy. The universe quite literally creates itself from nothing. The total energy of the universe is zero. Matter and radiation carry positive energy, but gravitational potential energy is negative. In a closed universe, these cancel exactly. The universe is the ultimate free lunch. It costs nothing to create. The mathematics works like this. In quantum mechanics, particles can tunnel through energy barriers they classically couldn't surmount. An electron facing a potential barrier has a small probability of appearing on the other side without having the energy to cross over the barrier. This is called quantum tunneling. It's been verified countless times in experiments. Tunneling makes many modern technologies possible, including the scanning tunneling microscope and flash memory in computers. Vilenkin applied this concept to the universe itself. Instead of a particle tunneling through a barrier, it's space-time tunneling from nothing into something. The barrier is the improbability of existence. On one side of the barrier is non-being. On the other side is a tiny, closed universe described by a particular geometry. Quantum mechanics allows tunneling from one state to the other. The probability is extremely low. But in quantum mechanics, low probability events happen constantly given enough opportunities. And in an infinite multiverse or eternal quantum foam, there are infinite opportunities. The tunneling universe starts infinitesimally small, much smaller than an atom, but it's not empty. It's filled with energy in the form of a cosmological constant or vacuum energy. This energy drives expansion. The universe inflates exponentially, growing from subatomic to cosmic scales in a fraction of a second. This is cosmic inflation. The tiny tunneled universe becomes large enough to contain everything we observe. This scenario resolves several puzzles. It explains why the universe began, not because something caused it, but because quantum mechanics allows it. It explains why the universe has zero total energy. That's the only kind of universe that can tunnel from nothing. It explains why the universe underwent inflation. That's what vacuum energy does. And it explains why we exist to ask the question. Only universes that inflate produce the structures necessary for life. But the quantum vacuum hypothesis raises new questions. What is the quantum vacuum? If it's truly nothing, how can it obey quantum mechanical laws? Laws require structure. Structure requires existence. So the vacuum isn't really nothing. It's a quantum state with definite properties. It can be described mathematically. It has an energy level, albeit zero. It has the potential to produce particle fluctuations. This is something, not nothing. Philosopher and physicist David Albert has criticized this approach. He argues that calling the quantum vacuum nothing is misleading. It's a highly structured entity governed by quantum field theory. The equations of quantum mechanics describe how it behaves. Those equations are not themselves nothing. They're abstract mathematical objects that exist in some sense. So the vacuum, plus the laws governing it, constitute a rather substantial something. If the quantum vacuum is not truly nothing, then we haven't explained creation from nothing. We've merely pushed the question back one level. Instead of asking what created the universe, we ask what created the quantum vacuum and the laws it obeys. Why does quantum mechanics exist? Why do its particular equations describe reality rather than different equations or no equations at all? These questions seem even harder than the original question about the Big Bang. Some physicists respond that laws of nature are not objects that exist in addition to physical systems. They're descriptions of how physical systems behave. The equations don't exist separately from the universe. They're part of the universe's structure. The quantum vacuum, governed by quantum mechanics, is the most fundamental level of physical reality. It requires no deeper explanation because there is no deeper level. It simply is what reality is made of at the most basic level. This moves the discussion into philosophy. Are mathematical laws discovered or invented? Do they exist independently of physical systems, or are they just useful descriptions? These questions have occupied thinkers for millennia. Platonists argue that mathematical objects exist in an abstract realm and physical reality instantiates them. Nominalists argue that mathematics is just a language we use to describe patterns in observations. The quantum vacuum hypothesis doesn't settle this debate. It inherits all the philosophical baggage. But it does provide a mechanism. If quantum fluctuations can produce virtual particles, and if the universe has zero net energy, then quantum fluctuations could produce the universe. The mechanism is well understood in other contexts. Extending it to cosmic scales is speculative but not arbitrary. It's an extrapolation of known physics into uncharted territory. Whether it's correct depends on quantum gravity, and quantum gravity remains an unsolved problem. What makes the quantum vacuum idea compelling is its economy. It requires minimal assumptions. Just quantum mechanics and general relativity, both well-tested theories. No gods, no prior universes, no exotic metaphysics. The universe emerges from quantum processes the same way particles do. This philosophical parsimony appeals to many scientists. It suggests reality at its base is simpler than it appears. Yet skeptics remain. They point out that calling zero energy nothing is a semantic trick. The quantum vacuum is a physical state with properties. Calling it nothing because the energy sums to zero is like calling a bank account with equal debits and credits non-existent. The account still exists, transactions still occur. Similarly, the quantum vacuum exists. Fluctuations occur, energy is borrowed and repaid. This is not nothing in any meaningful sense. The debate continues. But the quantum vacuum hypothesis demonstrates something important. Modern physics allows for processes that look like creation from nothing. Whether this is truly creation from absolute nothing or just creation from a pre-existing quantum state depends on definitions. But either way, the Big Bang doesn't require a transcendent cause. It can emerge from physical processes described by known laws. The universe creates itself. This is strange, but no stranger than much of quantum mechanics, and considerably less strange than many alternatives. Eternal inflation. The Big Bang wasn't a single event. It might have been one of countless events occurring continuously throughout eternity. This is the implication of inflation theory, one of the most successful ideas in modern cosmology, and it transforms the question of what created the Big Bang into something far more complex. Inflation was proposed by Alan Guth in 1980 to solve several problems in standard Big Bang cosmology. The universe is remarkably uniform on large scales. The cosmic microwave background has the same temperature in all directions to 1 part in 100,000. This uniformity is puzzling. Regions on opposite sides of the sky are so far apart that light hasn't had time to travel between them since the Big Bang. They've never been in casual contact. So how did they reach the same temperature? This is the horizon problem. Inflation solves it. In the first fraction of a second after the Big Bang, the universe expanded exponentially fast. Driven by vacuum energy, space doubled in size every 10^-37 seconds. This expansion was so rapid that a region smaller than an atom grew to astronomical size. Regions that are now on opposite sides of the observable universe were once close enough to interact and equilibrate. Then inflation stretched them apart. The uniformity we observe is a relic of pre-inflation conditions. Inflation also explains why the universe is so flat. The curvature of space is extremely close to zero. This requires fine-tuning in standard Big Bang models. But inflation stretches space so much that any initial curvature gets smoothed out. Like inflating a balloon makes its surface appear flatter locally. After sufficient inflation, the universe must be flat regardless of initial conditions. Observations confirm this. Space-time curvature is zero to within measurement precision. These successes made inflation a cornerstone of cosmology. But inflation has an unexpected consequence. Once it starts, it might never completely stop. This is eternal inflation. Here's why. Inflation is driven by a field called the inflaton. This field has an energy density. As the field rolls down its potential energy curve, it loses energy, and inflation slows. In most regions, inflation ends and normal expansion takes over. These regions become pocket universes, like ours. But quantum fluctuations affect the inflaton field. In some regions, fluctuations push the field back up its potential curve. Inflation re-accelerates in those regions. They expand exponentially, creating more volume. Within this new volume, most regions stop inflating, but a few, due to quantum fluctuations, continue. This process repeats forever. Inflation ends in most places, but continues in others. The inflating regions grow without bound. New pocket universes form continuously. This was demonstrated by Andrei Linde, Alexander Vilenkin, and others in the 1980s. They showed that under reasonable assumptions, inflation is eternal into the future. Once started, it cannot be stopped everywhere. It might end locally, but globally it continues. The multiverse of pocket universes grows forever, with new pockets constantly being created. Each pocket universe is a Big Bang. From inside a pocket, it looks exactly like our Big Bang. Hot, dense initial state. Rapid inflation ending in slower expansion. Formation of structures. Evolution toward complexity. Observers in any pocket see their pocket's creation as the beginning of everything, but from outside, it's just one event in an eternal process. This reframes the question of what created the Big Bang. The answer is inflation. Our Big Bang was a local end to inflation in this region of space. But inflation itself is ongoing elsewhere. So the real question becomes, what created inflation? And if inflation is eternal into the future, might it also be eternal into the past? If so, there's no beginning at all. Just an infinite process with no starting point. Vilenkin and colleagues investigated whether inflation can be eternal into the past. In 2003, Arvind Borde, Guth, and Vilenkin published a theorem. They proved that any eternally inflating universe must have a past boundary. The inflation cannot extend infinitely into the past. There must be a beginning of some kind. This theorem is rigorous. It follows from general relativity and basic assumptions about inflation. If the universe is eternally inflating into the future, it must have started at some finite time in the past. This seemed to restore the need for a beginning. Inflation must have begun somehow, but what caused it? The theorem doesn't specify. It only proves that a beginning exists. Some take this as evidence for a transcendent cause. Something outside physical law must have started inflation, but this conclusion doesn't follow. The theorem constrains inflation within space-time, described by general relativity. It doesn't rule out other scenarios. For example, inflation might have begun via quantum tunneling from nothing, as described earlier. Or it might have emerged from a pre-inflationary quantum state. Or the universe might have undergone a big bounce, contracting from a previous phase and rebounding into inflation. The Borde-Guth-Vilenkin theorem rules out certain eternal models, but doesn't specify what must replace them. The beginning of inflation remains unexplained. Eternal inflation also has implications for the nature of reality. If inflation creates infinite pocket universes, then every possible outcome of quantum processes occurs somewhere. The pockets differ in their detailed properties. Quantum fluctuations during inflation seed the structures in each pocket. These fluctuations are random, so different pockets have different initial conditions. Over infinite pockets, all possible initial conditions occur. Moreover, the laws of physics might vary between pockets. String theory suggests that the fundamental equations allow many solutions. Each solution describes a different vacuum state with different particle types, forces, and constants. These are like different phases of matter. Ice, water, and steam are all H2O, but with different properties. Similarly, different vacuum states are all solutions to the same underlying equations, but with different emergent physics. During inflation, different regions can settle into different vacua. This creates a multiverse where physical laws vary. Most pockets are inhospitable to life. Constants are wrong. Particles don't form stable atoms. Expansion is too fast or too slow, but some pockets, by chance, have conditions suitable for complexity. We obviously find ourselves in such a pocket. This is selection bias. Observers can only exist in observer-compatible pockets. This anthropic reasoning is controversial. Some scientists find it unsatisfying. It abandons the goal of predicting why the constants have specific values. Instead, it says they vary across pockets, and we observe particular values because only those values permit observers. This feels like giving up on an explanation, but others argue it's just accepting reality. If the multiverse is real, anthropic reasoning is unavoidable. We must account for selection effects. Ignoring them leads to incorrect inferences. Eternal inflation transforms cosmology from a historical science into a statistical one. We can no longer ask, why did the Big Bang have these properties? The question becomes, what is the probability distribution of properties across all pockets? Individual pockets are accidents. The ensemble is what matters. This shift is profound. It changes what counts as explanation. But eternal inflation also has problems. It predicts infinite pockets with all possible outcomes. This includes pockets where everything is identical to ours up to this moment but then diverges. Pockets where you exist but chose differently yesterday. Pockets where physics is different. The infinite diversity makes predictions difficult. Almost anything can be found somewhere in the multiverse. This threatens to make the theory unfalsifiable. If everything happens somewhere, what can we predict? Cosmologists working on eternal inflation are trying to address this. They develop measures to define typical observations in an infinite multiverse. They look for predictions that hold in most pockets. They search for observable signatures of eternal inflation, like patterns in the cosmic microwave background that indicate collisions between pockets. These are difficult problems, but progress is being made. Eternal inflation remains a serious proposal despite challenges. Whether eternal inflation is correct depends on the details of inflation itself. We don't know the exact mechanism. The inflaton field is hypothetical. We've never detected it directly. Alternative inflation models exist, some without eternal behavior. But eternal inflation is a natural consequence of the simplest inflation models combined with quantum mechanics. If inflation is real, eternal inflation is likely. And if eternal inflation is real, the Big Bang is not the beginning. It's one among infinitely many local starts to inflation's eternal process. The cyclic universe. What if the Big Bang was not a beginning but a transition? What if our universe emerged from the death of a previous universe? This is the cyclic model, an ancient idea revitalized by modern physics. It proposes that cosmic history is not a single chapter, but an endless book of expansions and contractions. The idea dates to ancient Hindu cosmology, which described cycles of creation and destruction spanning vast timescales. But modern versions are based on physics, not mythology. The central question is, can the universe collapse and re-emerge? Or does gravitational collapse always end in a singularity from which nothing can escape? Standard general relativity suggests collapse leads to singularity. If the universe's expansion slows, stops, and reverses, all matter and space converge toward a point. Density and temperature increase without limit. The Big Crunch mirrors the Big Bang in reverse. And at the crunch, physics breaks down just as it does at the bang. The singularity is a barrier. Classical physics cannot describe what happens there. So standard relativity cannot say whether anything follows a big crunch. The equations simply stop. But quantum mechanics might change this. Quantum effects prevent infinite density. The Heisenberg uncertainty principle forbids confining particles to infinitely small regions. As space contracts, quantum pressure builds. This pressure opposes gravity. At some point, quantum pressure could halt the collapse and trigger a rebound. Instead of a singularity, a bounce. The contracting universe reaches a minimum size, then begins expanding again. This is the big bounce. Loop quantum gravity, a leading quantum gravity theory, predicts exactly this. In loop quantum gravity, space-time is quantized. It's made of discrete units that cannot be subdivided. The universe can compress only so much before the quantized structure resists further compression. Calculations show that as density approaches the Planck scale, gravity becomes repulsive. The big crunch becomes a big bounce. The universe rebounds into a new expansion phase. This has been worked out in detail by Martin Bojuald and others. They modelled a contracting universe using loop quantum gravity equations. The collapse halts before reaching infinite density. The universe bounces. The rebound phase looks like a big bang. For observers in the expanding phase, It appears to be a beginning, but it's actually in the middle, a transition from contraction to expansion. If bounces are possible, the universe could be cyclic. Each expansion phase ends in contraction. Each contraction rebounds into new expansion. The cycle repeats eternally. Our Big Bang was one such bounce. Before it was a contracting phase. Before that, an expansion. Before that, a contraction. Infinitely into the past and future. No beginning, no end. Just eternal cycles. This solves the problem of what caused the Big Bang. The Big Bang wasn't caused. It was a phase transition in an eternal cyclic process. The question shifts from what started the universe to why is the universe cyclic? This might be easier to answer. Perhaps it's a necessary consequence of quantum gravity. Perhaps bounces are inevitable once you combine general relativity and quantum mechanics correctly. But cyclic models face challenges. The second law of thermodynamics states that entropy increases over time. Entropy measures disorder. The second law says the universe evolves toward maximum disorder. In our expanding universe, entropy increases steadily. Stars burn out. Black holes form. Eventually, heat death. But if the universe contracts and bounces, what happens to entropy? If entropy continues increasing through bounces, it must have been lower in previous cycles. Trace backward infinitely, and entropy goes to zero. But maximum order is an incredibly improbable state. An infinitely old cyclic universe should have reached maximum entropy long ago. We shouldn't observe the relatively low entropy universe we see. This is the entropy problem for cyclic models. One solution is to argue that entropy resets at each bounce. The bounce scrambles information. The rebounding universe starts fresh with low entropy. This requires physics beyond general relativity and quantum mechanics. Perhaps new processes at the Planck scale destroy information. Or perhaps the bounce connects to a baby universe with independent entropy. These ideas are speculative, but they show the entropy problem is not necessarily fatal. Another challenge is the cosmological constant. Our universe is dominated by dark energy, which drives accelerating expansion. If dark energy remains constant, the universe will never recollapse. It will expand forever, faster and faster. Contraction requires dark energy to be dynamic. Its density must decrease over time or reverse sign. Some models propose this. Quintessence models, for instance, feature evolving dark energy. But we have no evidence that dark energy changes. It appears constant. This makes future contraction unlikely. However, Paul Steinhardt and Neil Turok proposed a different cyclic model in 2002. Their model doesn't require contraction of our universe. Instead, it involves collisions between three-dimensional universes embedded in higher dimensional space. This is inspired by string theory, which proposes extra spatial dimensions. Ordinarily, these extra dimensions are tiny and undetectable, but in some string models, some dimensions are large. Our universe is a three-dimensional membrane, or brain, floating in higher dimensional space. In the Steinhardt-Turok model, two brains exist in the higher dimensional bulk. They attract each other. Over billions of years, they drift together. Eventually, they collide. The collision converts kinetic energy into matter and radiation. This creates a Big Bang on each brain. The brains bounce apart and drift back. The cycle repeats. Each collision is a new Big Bang. The bulk space is eternal. The cycles continue forever. This model has interesting features. It doesn't require inflation. The collision naturally produces a hot, dense, uniform state. Structure arises from quantum fluctuations during the approach phase. The model makes testable predictions about the cosmic microwave background that differ slightly from standard inflation. But observations to date support inflation. The Steinhardt-Turok model is not ruled out but is less favoured than inflationary models. Cyclic models also raise philosophical questions. If the universe is eternal, does it need a cause? Or is eternity self-sufficient? Some argue that an eternal universe avoids the need for explanation. It has no beginning, so nothing needs to start it. It simply exists, cycling forever. Others counter that existence still requires explanation. Why this cyclic process rather than nothing? Why these particular physical laws governing the cycles? Eternity doesn't eliminate the explanatory burden. It shifts it to questions of necessity and contingency. Roger Penrose has proposed yet another cyclic idea called conformal cyclic cosmology. He argues that the far future of our universe, after all matter decays and only photons remain, is mathematically equivalent to the Big Bang. Both states are conformally flat, meaning they have no intrinsic scale. Penrose suggests the end of one aeon matches the beginning of the next. The universe transitions from maximum entropy, heat death, to a new Big Bang. Time doesn't end or begin, it continues through the transition. This requires reinterpreting thermodynamics and gravity in radical ways. It remains highly speculative, but it demonstrates the variety of cyclic models. All aim to eliminate the singularity. All propose that the Big Bang is not a beginning but a transition. And all struggle with entropy, observational constraints, and the need to go beyond known physics. Cyclic models appeal because they resolve the beginning problem by denying there was a beginning. They replace a singular creation event with eternal process. This feels more parsimonious to some. No need for transcendent causes. The universe just is, cycling forever. But this intuition is not universally shared. Others find beginnings less problematic than infinities. An eternal past seems to require infinite information and infinite fine-tuning. Better to have a beginning, even if we don't understand what caused it. The debate continues. Cyclic models remain viable alternatives to single Big Bang cosmologies. Whether they're correct depends on quantum gravity, the nature of dark energy, and features of the very early universe. We need better data and better theories. Until then, cyclic universes remain an intriguing possibility. They suggest the Big Bang, far from being the beginning of everything, might have been just another beat in an eternal cosmic rhythm. The multiverse and probability. If multiple universes exist, each with its own Big Bang, then asking what caused the Big Bang becomes strange. There's no single Big Bang to explain. Instead, there are countless Big Bangs, each with potentially different causes or no cause at all. This multiverse perspective reshapes the entire question, and it introduces new puzzles about probability and existence. The multiverse is not a single theory, it's a prediction of multiple theories. Eternal inflation predicts bubble universes. String theory predicts different vacuum states. Quantum mechanics, interpreted via many worlds, predicts branching realities. Each framework generates multiplicity through different mechanisms. But all share a common feature. They make our universe just one among many. In eternal inflation's multiverse, each pocket universe has its own Big Bang. These events are not causally connected. They occur independently in different regions of inflating space. From inside any pocket, the Big Bang appears to be the beginning. But from the inflating bulk, it's a local transition. The creation of one pocket doesn't explain the creation of another. Each is a separate quantum event. This has implications for explanation. If our Big Bang is one of infinitely many, it doesn't need a unique cause. It's a statistical occurrence. Like radioactive decay, where individual atoms decay randomly, but the half-life is predictable. No one asks what caused this particular atom to decay at this moment. It's a quantum event with a probability, not a deterministic outcome. Similarly, our Big Bang might be a quantum event. It happened because such events happen probabilistically given inflation. No further cause is needed. But this raises a new question. Why these initial conditions rather than others? In an infinite multiverse, all possible initial conditions occur somewhere. But some conditions are more common than others. The probability distribution matters. If we want to explain our observations, we need to know whether our universe is typical or atypical within the distribution. This is where anthropic reasoning enters. We observe certain conditions, not because they're common, but because they're necessary for observers. If 99.99% of universes are sterile, that doesn't matter. We can only exist in the 0.01% where conditions permit life. Our observations are selection biased. We sample only observer-compatible regions of the multiverse. This logic explains apparent fine-tuning. The cosmological constant in our universe is extremely small compared to theoretical predictions. It's fine-tuned to 120 decimal places. This seems absurdly improbable, but in a multiverse with varying constants, this value must occur somewhere, and observers can only emerge in regions where it's small enough for galaxies to form. We observe a small cosmological constant because large values don't permit observers. Similar reasoning applies to other constants. The strength of the strong nuclear force, the mass of the electron, the ratio of protons to neutrons, all appear fine-tuned. But if they vary across the multiverse, the fine-tuning is explained by selection. We're in a rare pocket where the conditions are right, not because the universe was designed for us, but because we can only exist in universes compatible with our existence. Critics argue this is non-predictive. If everything happens somewhere, any observation can be explained. The multiverse becomes unfalsifiable. But defenders counter that anthropic predictions are testable. If a constant must be fine-tuned for observers, we predict it will be near the minimum viable value, not much more precise than necessary, because more precise fine-tuning is rarer and thus less likely to be observed. The cosmological constant fits this pattern. It's small enough for galaxies, but not smaller. This matches anthropic expectations. Moreover, the multiverse is not ad hoc. It's predicted by independently motivated theories. Inflation solves cosmological problems and predicts eternal behavior. String theory unifies forces and requires multiple vacua. Many worlds follow from taking quantum mechanics literally. These theories have reasons to be believed beyond explaining fine-tuning. The multiverse is a consequence, not an assumption. This makes it scientifically respectable. But the multiverse raises disturbing questions about probability. If infinitely many observers exist across infinitely many universes, what does it mean to be you? In an infinite multiverse, infinitely many exact copies of you exist, infinitely many near copies who differ in one decision, infinitely many distant versions living completely different lives but still recognizably related. Which one are you? The question seems meaningless. You are obviously this instance, reading this now, with these memories, but from a multiverse perspective, that's just an indexical reference. Like saying, I am here. It's true, but doesn't pick out anything unique. Infinitely many versions can say the same thing. So what makes this instance special? Nothing. It's just one among infinitely many. This has implications for decision theory. If every choice you make is also made differently by other versions of you, does choosing matter? Your individual choice doesn't change the total number of outcomes. They all happen anyway. Some philosophers argue this makes decision-making meaningless. If all paths are taken, why care which path you take? Others respond that this confuses levels. From a God's eye view, all outcomes occur. But from your subjective perspective, only one path matters, yours. You still experience consequences. You still have preferences. The fact that other versions choose differently is irrelevant to your lived experience. Caring about your choices is not invalidated by the existence of other choosers. Another puzzle is the measure problem. In an infinite multiverse, everything happens infinitely many times. So how do you compare probabilities? Is a universe where something happens 1 trillion times more probable than one where it happens 1 million times? Not really. Both happen infinitely often. Standard probability measures don't work with infinite sets. You need a cutoff or weighting scheme. But which one? Different choices give different answers. There's no consensus on the right measure. This problem plagues multiverse cosmology. Predictions depend on measure choices. The arrow of time. Time flows in one direction, past to future. Causes precede effects. Entropy increases. We remember yesterday, but not tomorrow. This asymmetry seems obvious, but physics doesn't explain it. The fundamental laws work equally well forward and backward in time. So why does time have an arrow? And what does this tell us about the Big Bang's origin? Newton's laws are time symmetric. If you film a planet orbiting a star and play the video backward, it still obeys the equations. The same is true for Maxwell's equations of electromagnetism, Einstein's general relativity, and quantum mechanics. The fundamental laws don't distinguish the past from the future. They're reversible. Yet our experience is deeply asymmetric. Eggs break but don't unbreak. Stars radiate energy but don't absorb it from everywhere. We age forward, never backward. The only fundamental law that's not time symmetric is the second law of thermodynamics. It states that entropy, a measure of disorder, increases over time in closed systems. This gives time its direction. The future is the direction of increasing entropy. The past is the direction of lower entropy. But the second law is not truly fundamental. It's statistical. It emerges from the behavior of large numbers of particles. Consider a box of gas. The molecules bounce around randomly. At any moment, most configurations have molecules spread evenly throughout the box. A few rare configurations have all molecules in one corner. If you start with molecules in one corner, they'll spread out. Entropy increases, but the underlying collisions are reversible. Each collision could run backward. The spread out gas could spontaneously concentrate. It's just overwhelmingly improbable. The second law is about probability, not impossibility. Entropy can decrease. It's just extremely unlikely. In a small system, fluctuations happen. Molecules temporarily cluster. But in large systems, like the universe, such fluctuations are negligible. Entropy increases because high entropy states vastly outnumber low entropy states. Given random motion, systems evolve toward typical states, and typical states have high entropy. This explains why time has an arrow, but it creates a puzzle. If entropy increases toward the future, it must have been lower in the past. Trace backward, and entropy decreases all the way to the Big Bang. The early universe was extremely ordered. Matter and energy distributed smoothly, temperature nearly uniform. This is a very low entropy state. Why? This is called the past hypothesis. The universe began in an extraordinarily improbable low entropy configuration. From there, entropy has been increasing ever since. The second law follows from this initial condition, but the initial condition itself demands explanation. Why did the Big Bang produce a low entropy universe rather than a high entropy mess? High entropy is more probable. The universe should have started that way, but it didn't. Some argue that gravity changes the analysis. In a universe without gravity, gas spread evenly is maximum entropy. But with gravity, gas spread evenly is unstable. It collapses into clumps. Stars, galaxies, black holes form. These structures represent higher entropy than smooth gas. So perhaps the early universe, though smooth, wasn't actually low entropy when gravity is considered. The Big Bang was high entropy, and entropy has been increasing through structure formation. But this doesn't work. Roger Penrose calculated the entropy of the early universe compared to possible late universe states dominated by black holes. He found the Big Bang had incredibly low entropy, about 1 part in 10 to the power of 10 to the power of 123. This is an unimaginably small probability. The universe could have started in vastly more probable high entropy states, but it didn't. It started in one of the most improbable states possible. Why? No one knows. This is one of the deepest mysteries in cosmology. Some suggest the answer lies in quantum gravity. Perhaps the Big Bang wasn't actually a singularity. Perhaps it was a bounce from a previous contracting phase. In a contracting universe, entropy would increase as matter clumps and black holes form. But at the bounce, something resets the clock. The new expanding phase starts with low entropy again. Others propose that the low entropy beginning is selection bias. In a multiverse, most universes start with high entropy and nothing interesting happens. But observers can only emerge in low entropy universes where complexity can develop. We find ourselves in a low entropy universe because high entropy universes don't produce observers. This is another application of anthropic reasoning, but this feels unsatisfying to many. It explains observation through selection rather than mechanism. It doesn't tell us how the low entropy state was produced, just that we must observe it if we observe anything. Some physicists argue that this is the best explanation available. Others continue searching for a dynamical mechanism that produces low entropy naturally. The arrow of time also relates to causation. We say causes precede effects. But why? The laws of physics don't prefer one time direction over another. The connection between causation and time's arrow is not understood. Some philosophers argue that causation defines time's direction rather than the reverse. The future is the direction in which causes produce effects. But this seems circular. What makes something a cause rather than an effect, if not temporal priority? Quantum fluctuations and reality. The universe might not have been created at all. It might have simply fluctuated into existence from nothing. This is not metaphor or mysticism. It's a prediction of quantum field theory, and it suggests that the question, what created the Big Bang, is based on a false premise. Creation implies a process, but quantum events don't have processes, they just happen. Quantum mechanics describes reality as fundamentally probabilistic. An electron doesn't have a definite position until measured. It exists in a superposition of possibilities. When measured, it appears at one location. But which location is random? The theory gives probabilities, not certainties. This indeterminacy is not due to ignorance. It's a fundamental feature of nature. Reality at the quantum level is irreducibly uncertain. This uncertainty extends to the vacuum. Empty space is not actually empty. It's filled with quantum fields. These fields fluctuate constantly. Virtual particles pop into existence and disappear. These fluctuations have been measured. They affect atomic energy levels. They create pressure between metal plates. The Casimir effect, the Lamb shift, the anomalous magnetic moment of the electron all depend on vacuum fluctuations. The quantum vacuum is real and active. If the vacuum can produce particles, perhaps it can produce universes. This was Edward Tryon's proposal in 1973. He suggested the entire universe is a quantum fluctuation of the vacuum, not a small fluctuation, the biggest one possible. The universe emerged from nothing via quantum tunneling. It sounds absurd, but mathematics supports it. Here's how it works. The total energy of the universe might be exactly zero. Matter and radiation have positive energy. Gravity has negative potential energy. In a closed universe, these cancel precisely. Creating the universe costs no energy. It's the ultimate free lunch. Quantum mechanics allows energy to fluctuate from zero as long as it returns to zero. The uncertainty principle permits temporary energy imbalances. Larger imbalances last shorter times. But if the net energy is zero, the imbalance can last forever. So the universe fluctuates into existence with zero total energy. It expands, driven by inflation. The expansion creates space and matter, but the total energy remains zero. Gravity's negative contribution exactly balances matter's positive contribution. The universe exists because quantum mechanics allows it. No cause is needed. Quantum events don't have causes. They have probabilities. The universe happened because it was possible, and quantum mechanics makes it possible. This explanation troubles many people. It seems to get something from nothing, but nothing in physics means empty space with quantum fields, not absolute nothingness. The vacuum is a quantum state. It has properties. It obeys laws. It's something, not nothing. So the universe didn't come from absolute nothingness. It came from a quantum vacuum, which is a physical entity. But this raises the question, where did the quantum vacuum come from? If the vacuum is governed by quantum field theory, where did that theory come from? We haven't eliminated the creation problem. We've just pushed it back to the laws of physics. Why do these laws exist rather than different ones? Or no laws at all? Quantum fluctuation accounts for the universe, but not for quantum mechanics itself. Alexander Vilenkin addressed this by proposing that the universe tunneled from literally nothing, not from a quantum vacuum, from absolute non-existence. His model describes this using the Wheeler-DeWitt equation, which treats the universe's wave function. He showed that a universe can tunnel from a state with no space, no time, no matter, into a state with all of those. The mathematics is rigorous. Whether it describes reality is unknown. Critics point out that the Wheeler-DeWitt equation is itself a physical law. It exists, it has structure, so even Vilenkin's nothing isn't truly nothing. It's a mathematical structure capable of producing universes. Some argue this shows that true creation from nothing is impossible. There must always be some pre-existing structure. Whether that structure is physical like the vacuum or abstract like mathematics, something must exist for a universe to emerge from it. But quantum mechanics does suggest that existence is more permissive than classical physics implies. In classical physics, energy must be conserved absolutely. You cannot create something from nothing. But in quantum mechanics, energy can fluctuate temporarily. Virtual particles borrow energy, exist briefly, and disappear. Scale this up cosmically, and perhaps whole universes fluctuate into existence. Most collapse immediately, but occasionally one inflates and becomes permanent. We're in such a universe because the collapsed ones don't permit observers. This also addresses the fine-tuning problem. If universes are quantum fluctuations, there should be many of them with different properties. Most fluctuations produce uninhabitable universes. They're too hot, too cold, too small, or their constants are wrong. But some fluctuations produce viable universes. We're in one because we couldn't be in the others. The multiverse emerges naturally from quantum fluctuation, and with it, anthropic explanations for fine-tuning. The quantum fluctuation hypothesis also has theological implications. Many religious traditions hold that God created the universe, but if the universe is a quantum fluctuation, no creator is needed. The laws of quantum mechanics suffice. This doesn't disprove God. Perhaps God established the laws that permit fluctuations, but it does eliminate the need for direct divine intervention. The universe creates itself through natural processes. Some theists respond that quantum laws still require explanation. Why does quantum mechanics exist? Why are the laws structured to permit universe-creating fluctuations? These questions point to a deeper level that might involve God or some necessary being. But this moves God further from the action. Instead of creating the universe directly, God creates the laws that create the universe, or creates the mathematical structures that instantiate the laws. This is deism rather than traditional theism. Others argue that quantum fluctuation is compatible with creation theology. Perhaps God's creative act is precisely the establishment of quantum mechanics. The fluctuation is the mechanism of creation, not an alternative to it. This makes creation less mysterious and more scientifically understandable. But it preserves the theological claim that existence depends on something beyond the physical. These debates continue with no resolution in sight. What's clear is that quantum mechanics makes the origin question more tractable. Instead of requiring a singular cause at a specific moment, it allows universes to emerge probabilistically from quantum vacuum states. This doesn't answer every question. The laws themselves still need explanation, but it provides a mechanism consistent with known physics. The Big Bang could be a quantum event, like radioactive decay or particle tunneling, an uncaused event permitted by quantum indeterminacy. This reframes the whole discussion. The question changes from what caused the Big Bang to what makes Big Bangs possible. The answer is quantum mechanics plus appropriate energy conditions. Whether these are realized in a single universe or a multiverse, quantum fluctuation provides a causeless origin. The universe doesn't require a creator. It requires only that the laws of physics permit self-creation. And according to quantum field theory, they do. String theory and hidden dimensions. The Big Bang happened in more than 3 spatial dimensions. This sounds absurd. We experience 3 dimensions of space. Up, down, left, right, forward, backward. Adding more seems nonsensical. But string theory, the leading candidate for quantum gravity, requires additional spatial dimensions. And these extra dimensions might explain what triggered the Big Bang. String theory proposes that fundamental particles are not point-like, they're tiny vibrating strings. Different vibration patterns produce different particles. An electron is one vibration mode. A quark is another. Photons, neutrinos, all particles emerge from strings vibrating in various ways. This idea unifies all forces and particles into a single framework. Gravity, electromagnetism, the strong and weak nuclear forces all arise from string dynamics. But mathematics only works in 10 dimensions, not 4, which is what we observe, 10. 9 spatial dimensions plus time. If string theory is correct, 6 extra spatial dimensions exist beyond the 3 we see. Why don't we notice them? Because they're compactified, curled up into shapes so tiny that we cannot detect them, like a garden hose. From far away, it looks one-dimensional, but up close, you see it has a circular cross-section. The hose is actually two-dimensional. One dimension is large, the other is tiny and curled. Similarly, the universe has 3 large spatial dimensions and 6 tiny ones. The tiny dimensions are compactified at the Planck scale, around 10⁻35 meters. We cannot resolve structures that small, so we don't see the extra dimensions. They're there, affecting particle physics, but invisible to macroscopic observation. The shape of these extra dimensions matters. Different compactifications produce different physics. The 6 dimensions can curl up in countless ways. Each shape corresponds to a different vacuum state, with different particle masses and coupling constants. String theory doesn't predict a unique universe. It predicts a landscape of possibilities, perhaps 500 different vacuum states. Each is a valid solution to the equations. Each describes a different possible physics. This connects to the multiverse. If eternal inflation is real, different regions can settle into different string theory vacua. Each pocket universe has its own compactification, its own physics. The landscape of string theory vacua becomes realized across the multiverse. Our universe occupies one point in this vast landscape. Neighboring pockets occupy different points with different laws. But how does this explain the Big Bang? The answer involves brane collisions. In string theory, extended objects called branes exist alongside strings. Branes are like membranes. They can be one-dimensional, two-dimensional, or higher. Our entire universe might be a 3-dimensional brane embedded in higher dimensional space. The extra dimensions are the bulk. The brane is our 3-dimensional slice through it. If multiple branes exist in the bulk, they can move, and they can collide. Paul Steinhardt and Neil Turok developed this into a cosmological model. They proposed 2 3-dimensional branes parallel to each other in the bulk. These branes attract each other through gravity, acting in the extra dimensions. Over billions of years, they drift together. Eventually, they collide. The collision converts kinetic energy into matter and radiation on each brane. This creates a hot, dense state. Expansion begins. From the perspective of observers on the brane, this looks exactly like the Big Bang. The collision is the triggering event. It explains what caused the Big Bang without invoking singularities or creation from nothing. The Big Bang was a collision between branes in higher dimensional space. This model has several attractive features. It doesn't require inflation. The collision naturally produces a hot, uniform state. Structure arises from quantum fluctuations during the approach phase before collision. The model makes predictions about the cosmic microwave background that differ slightly from inflation. Specifically, it predicts more tensor modes. These are gravitational waves from the early universe. Observations constrain tensor modes. Current data favor inflation over the brane collision model, but future experiments might change this. The cyclic version of this model proposes that branes collide repeatedly. After collision, they bounce apart, then drift back together, collide again. Each collision is a new Big Bang. The cycle continues eternally. This eliminates the beginning problem. The branes and bulk are eternal. Big Bangs are periodic events within an eternal substrate. But string theory remains unconfirmed. Despite decades of work, no experimental evidence supports it. The theory makes predictions, but they involve energies far beyond current accelerators. Testing string theory directly seems impossible with foreseeable technology. Some critics argue this makes string theory unfalsifiable. If we cannot test it, is it science? Defenders respond that string theory makes mathematical sense of quantum gravity. That alone makes it worth studying. The extra dimensions predicted by string theory might be detectable indirectly. If they exist, gravity should leak into them at short distances. This would modify Newton's law at sub-millimeter scales. Experiments have looked for such deviations, none found so far. But the negative results constrain how large extra dimensions can be. They must be smaller than about 1 millimeter. This doesn't rule out string theory. The extra dimensions could be much smaller, but it eliminates some versions. Another possible signal is microscopic black holes. If extra dimensions exist and are relatively large, particle colliders could produce tiny black holes. These would decay immediately via Hawking radiation. The decay signature would be distinctive. The Large Hadron Collider looked for such events. None were observed. This constrains extra dimension models, but again doesn't eliminate them. The dimensions might be too small for LHC energies to probe. String theory also predicts new particles, supersymmetric partners for all known particles, a superpartner for the electron called a selectron, a superpartner for the quark called a squark. These particles could be dark matter. They interact weakly and have the right properties. But no supersymmetric particles have been discovered. This doesn't disprove supersymmetry. The particles might be too heavy for current colliders, but it reduces confidence in the theory. Despite these challenges, string theory remains the best framework for quantum gravity. It's the only theory that successfully describes gravity at quantum scales. The mathematics is beautiful and consistent. It unifies forces elegantly. Many physicists believe it's at least pointing in the right direction. Whether it's the final theory or a stepping stone to something deeper remains unknown. For the question of what created the Big Bang, string theory offers a specific mechanism: brane collisions in higher dimensional space. This is speculative, unconfirmed, based on a theory that itself lacks experimental support, but it demonstrates that physics can address creation questions without invoking anything supernatural. Extra dimensions and brane dynamics are natural consequences of trying to unify quantum mechanics and gravity. If the mathematics is correct, they're real. And if they're real, they provide a causal mechanism for the Big Bang, the holographic principle. The universe might be a hologram, not metaphorically, literally. All the information in three-dimensional space could be encoded on a two-dimensional surface. This is the holographic principle, one of the strangest ideas in theoretical physics, and it has profound implications for understanding the Big Bang. The holographic principle emerged from black hole physics. In the 1970s, Jacob Bekenstein discovered that black holes have entropy. Entropy measures the number of possible microstates corresponding to a macroscopic state. For ordinary objects, entropy is proportional to volume. More volume means more places for atoms to arrange themselves. More arrangements mean more entropy. Double the volume, double the entropy. But black holes are different. Bekenstein showed that a black hole's entropy is proportional to its surface area, not its volume. Specifically, the entropy equals 1/4 the area of the event horizon measured in Planck units. This is called the Bekenstein bound. It sets a limit on how much information can be contained in a region of space. Why area instead of volume? Stephen Hawking's black hole radiation provided a clue. Black holes emit thermal radiation. As they radiate, they lose mass and shrink. Eventually, they evaporate completely. But thermal radiation appears random. It carries no information about what fell into the black hole. If information is destroyed, quantum mechanics is violated. This is the black hole information paradox. Gerard Hooft and Leonard Susskind proposed a solution. Information isn't destroyed, it's never fully inside the black hole. Instead, it's encoded on the event horizon. The horizon is a two-dimensional surface, but it contains all the information about the three-dimensional interior. Like a hologram, which encodes three-dimensional images on two-dimensional film, the black hole is a hologram. The interior is a projection from the surface. This idea was generalized to the universe as a whole. Perhaps all three-dimensional space is a hologram. All the information in the universe is encoded on a distant two-dimensional surface. That surface is the cosmic horizon, the boundary of the observable universe. Everything we see, every particle, every force, is a projection from information stored on that distant surface. This sounds crazy, but it's supported by mathematics. The AD-S CFT correspondence, discovered by Juan Maldacena in 1997, proves that certain string theories in higher dimensions are equivalent to quantum field theories in lower dimensions. The theories are dual. They describe the same physics from different perspectives. This is holography made precise. The bulk space emerges from boundary dynamics. If the universe is a hologram, what does this mean for the Big Bang? It suggests that the Big Bang was not an event in three-dimensional space. It was a process on a two-dimensional surface. The expansion we observe is the unfolding of information encoded on the boundary. The three-dimensional universe is a projection that grows as more information becomes accessible. This reframes the creation question. Instead of asking what happened at the singularity, we ask what happened on the boundary. The boundary might not have a singularity. It might be smooth. The apparent singularity in the bulk is an artifact of the projection, like how a hologram can show a point that doesn't exist on the film itself. The point is constructed by interference patterns on the surface. Some versions of the holographic principle suggest that time itself is emergent. The boundary theory might be timeless. Time appears only in the bulk projection. If so, asking what happened before the Big Bang is meaningless. There is no time direction on the boundary. The temporal structure of the universe emerges from spatial structure on the boundary. Past and future are features of the projection, not the fundamental reality. This connects to quantum gravity in interesting ways. If space is emergent from boundary information, then space-time geometry is not fundamental. It's derived from more basic entities. Perhaps entanglement patterns in the boundary theory? Quantum entanglement creates connections between distant points. These connections might generate the appearance of spatial geometry when viewed from the bulk perspective. Mark van Ramsdonk and others have developed this idea. They showed that entanglement entropy in the boundary theory corresponds to minimal surfaces in the bulk. More entanglement means more connected geometry. Less entanglement means geometry fragments. Space itself might be woven from quantum entanglement. Without entanglement, there's no space, just isolated points with no notion of distance or adjacency. If space emerges from entanglement, then the Big Bang might be the moment when entanglement became sufficient to generate connected geometry. Before that, no space existed. Not because there was nothing, but because the boundary information wasn't organized into spatial form. The Big Bang was not creation from nothing, it was organization from chaos. A phase transition on the boundary that projected into the bulk as expanding space. This provides a new perspective on initial conditions. Instead of requiring low entropy at the Big Bang, we might need specific entanglement patterns on the boundary. The boundary state determines bulk physics. Different boundary states produce different cosmologies. Our Big Bang corresponds to one particular boundary configuration. Other configurations produce other universe histories. Testing the holographic principle is difficult. It makes few direct predictions about observable phenomena, but it does constrain quantum gravity theories. Any viable quantum gravity must incorporate holography. Theories that violate the Bekenstein bound are inconsistent. This eliminates many possibilities. Holography is a guiding principle for constructing quantum gravity. Some speculative ideas propose detecting holographic structure directly. If the universe is a hologram with finite resolution, there might be granularity in space-time at small scales. Experiments look for this. So far, nothing found. But the search continues. If space-time is emergent from boundary information, that information must be encoded somehow. The encoding might leave signatures. The holographic principle also affects cosmology more broadly. If the universe's information is bounded by surface area, then the maximum entropy is finite. This constrains evolution. The universe cannot increase entropy indefinitely if total entropy is capped. This might prevent heat death or change its nature. Instead of entropy increasing forever, it might reach a maximum and saturate. What happens then is unknown. Some propose that the cosmological constant, dark energy, is related to holography. The cosmic horizon has finite area due to accelerating expansion. This area bounds the universe's entropy. Perhaps dark energy exists precisely to maintain this bound. The cosmological constant's value sets the horizon size. The horizon size sets maximum entropy. Everything is connected through holographic relations. These ideas remain speculative, but they demonstrate how deeply holography affects fundamental physics. It's not just an interesting mathematical curiosity. It's a principle that reshapes our understanding of space, time, information, and gravity. And it offers new ways to think about the Big Bang, not as a temporal beginning, but as a boundary condition, not as creation from nothing, but as projection from information. The universe doesn't start, it unfolds, consciousness and observation. The Big Bang might require observers. This sounds insane. How can observation affect events that happened billions of years before observers existed? But quantum mechanics forces us to consider this possibility, and it leads to one of the strangest explanations for why the universe exists. Quantum mechanics describes particles as existing in superposition, multiple states simultaneously. An electron spins both clockwise and counterclockwise until measured. Measurement collapses the superposition. The electron definitely becomes spin up or spin down. But what counts as measurement? Does it require consciousness, or do any interactions collapse superposition? The orthodox Copenhagen interpretation sidesteps this question. It treats measurement as a primitive concept. Systems have wave functions that evolve deterministically. Measurements yield outcomes probabilistically. The wave function collapses upon measurement, but what measurement means physically is left undefined. This has bothered physicists for decades. The many worlds interpretation eliminates collapse. Superpositions never collapse. Instead, the universe branches. Each outcome occurs in a separate branch. Measurement doesn't reduce possibilities. It differentiates them across parallel realities. But this requires accepting countless parallel universes. Most physicists find this extravagant. Another interpretation involves consciousness directly. Perhaps consciousness collapses wave functions. Physical interactions merely entangle systems. But conscious observation selects one outcome. This is the von Neumann-Wigner interpretation. It makes consciousness fundamental to physics. Without observers, the universe remains in superposition. Observation actualizes one possibility from many. If consciousness collapses wave functions, then the early universe was entirely in superposition. Multiple Big Bangs occurred simultaneously. Different expansion rates, different constants, different structures, all coexisted in quantum superposition. When the first conscious observers emerged billions of years later, they collapsed this superposition retroactively. Their observations selected which Big Bang had occurred. This is called the participatory anthropic principle, proposed by John Wheeler. Observers participate in creating the universe by observing it. The act of observation extends backward in time, selecting the history that led to the observer. The universe exists because it's observed, and observation requires observers to emerge. So the universe must have properties that permit observers. This explains fine-tuning through a temporal loop. This sounds like science fiction, but it's based on real quantum phenomena. Delayed choice experiments demonstrate that measurement can affect the past. A photon passes through a double slit. You decide after it passes whether to measure which slit. Your future measurement determines whether the photon's past behavior was wave-like or particle-like. The experiment works. The past is indeed affected by future measurement choices. Scale this up cosmically. The universe passes through quantum crossroads early in its history. Which path it took remains undetermined until observed. Billions of years later, observers emerge. Their existence collapses the cosmic wave function retroactively. The Big Bang they observe is the one that permits observers. Other Big Bangs occurred in superposition but weren't actualized. This explanation is deeply strange. It makes consciousness cosmically significant, not in some vague spiritual sense, in a precise physical sense. Without consciousness, the universe doesn't exist. Not because consciousness creates matter, but because it selects reality from superposition. Before observation, there are only possibilities. Observation makes one possibility actual. Critics argue this is mysticism disguised as physics. Consciousness is not well defined. We don't know what it is or how it relates to physical processes. Using consciousness to explain quantum mechanics and cosmology is explaining the obscure by the more obscure. It doesn't solve problems, it multiplies them. Defenders respond that consciousness is no more mysterious than quantum mechanics itself. Both are fundamental features of reality. Perhaps they're related. Perhaps the measurement problem and the hard problem of consciousness are connected. Solving one might solve the other. This is speculation, but it's not obviously wrong. Another version avoids consciousness explicitly. It proposes that any sufficiently complex information processing system can collapse wave functions. Computers, brains, sophisticated machines. Anything that processes information selects outcomes from superposition. The universe remained quantum until complexity emerged. Then information processing began. Reality crystallized as processing systems multiplied. This is more palatable to physicists uncomfortable with consciousness. It grounds wave function collapse in information theory rather than subjective experience. But it still makes the Big Bang dependent on subsequent developments. The early universe was indeterminate. Later information processing made it determinate retroactively. These observer-dependent cosmologies solve certain problems. Fine-tuning becomes expected because fine-tuning is necessary for observers. the universe must permit observers to be observed. Only observer-compatible universes get actualized. Universes incompatible with observers remain forever in superposition, unobserved and thus unreal. But they create new problems. If observation selects reality, then multiple realities might be selected by different observers. Your observation collapses the wave function one way, mine collapses it another. Do we experience different universes? Or does some collective observation process create consensus reality? The participatory principle also strains causality. Normally, causes precede effects. But if observation affects the past, effects can precede causes temporally. The observer creates the conditions for their own existence. This bootstrapped paradox appears throughout observer-dependent cosmologies. It's either profound or absurd, depending on your philosophical inclinations. John Wheeler took this seriously until his death. He believed observers genuinely participate in creating cosmic history. The universe is not a clockwork mechanism running independent of observation. It's a participatory reality where consciousness plays an irreducible role. This transforms the Big Bang from an objective historical event into something more subtle and observer-dependent. Most physicists reject this. They argue consciousness is irrelevant to quantum mechanics. Decoherence, the interaction with the environment, causes apparent collapse without requiring observers. The universe existed long before consciousness emerged. To suggest otherwise inverts causality absurdly. But the minority who take observer-dependent models seriously point out that we cannot prove the universe existed unobserved. All evidence comes from observation. We reconstruct the past from present measurements. Perhaps that reconstruction is the reality. Perhaps the past doesn't exist independently of being observed. This sounds radical, but quantum mechanics is radical. Perhaps cosmology should be too. Mathematical Platonism and existence. Numbers exist, not physically, but they exist. 2 + 2 = 4, regardless of whether anyone calculates it. Mathematical truths are discovered, not invented. This is mathematical Platonism. And it offers a surprising answer to what created the Big Bang, mathematics itself. Consider the Pythagorean theorem. It's true for right triangles on Earth, on Mars, in distant galaxies. It was true before humans existed. It will be true after we're gone. The theorem doesn't depend on physical instantiation. It's true abstractly, in itself, independent of the universe. This suggests mathematical objects exist in some non-physical realm. Plato argued that abstract forms are more real than physical objects. A physical triangle is an imperfect copy of the ideal form of triangle. The form exists eternally and perfectly. Physical triangles are temporary shadows. Modern Platonists apply this to mathematics generally. Numbers, equations, and geometric objects exist abstractly. The physical world instantiates these abstractions imperfectly. If mathematical objects exist independently, then mathematical truths govern reality from outside. The universe obeys mathematical laws, not because the laws are descriptions we invented, but because mathematical structure is ontologically prior. Physics is applied mathematics. The universe is mathematics made concrete. Max Tegmark pushed this idea to its logical conclusion. He proposed the mathematical universe hypothesis. Every mathematically consistent structure exists physically, not just as an abstraction, but as a real universe. Our universe is one such structure, a particular solution to certain equations. Other solutions also exist as other universes. The multiverse is the set of all mathematical structures. This explains why mathematics describes physics so well. Physics is mathematics. Particles, forces, and space-time are mathematical objects. They obey equations because they are equations. An electron isn't described by mathematics. It is a mathematical structure instantiated as physical reality. There's no gap between map and territory because the territory is the map. Under this view, asking what created the Big Bang is like asking what created the number 7. The question is confusing. Mathematical structures don't get created. They exist necessarily as abstract objects. The universe, being a mathematical structure, also exists necessarily. It wasn't created, it simply is, timelessly, as part of the mathematical landscape. But this raises new questions. Why this mathematical structure rather than others? If all structures exist, why do we experience this one? Tegmark argues we experience this universe because it permits observers. Most mathematical structures are too simple or too chaotic for complexity. Only special structures support consciousness. We find ourselves in one because we couldn't find ourselves anywhere else. This brings anthropic reasoning back through a mathematical door. Fine-tuning is explained not by luck or design, but by necessity. All mathematical structures exist. Most don't support observers. We necessarily observe one that does. The selection isn't mysterious. It's a logical necessity given that observation requires observers. Critics attack this from multiple angles. First, not all mathematicians are Platonists. Many argue mathematics is invented, not discovered. It's a language humans created to describe patterns. Useful, powerful, unreasonably effective, but still human creation, not transcendent reality. If mathematics is invented, it can't explain the universe's existence. That inverts the explanation. Second, even accepting Platonism, abstract existence differs from physical existence. Numbers might exist abstractly without existing physically. The number 7 doesn't weigh anything. It doesn't occupy space. It's not made of particles. Saying the universe is a mathematical structure doesn't explain how abstract structures become physical. The hard problem remains. Third, the claim that all mathematical structures exist physically is extraordinary. It multiplies entities wildly beyond necessity. Why believe in infinite, physically real universes just to avoid saying our universe is special? Occam's razor suggests simpler explanations. One universe requiring explanation is better than infinite universes requiring explanation. Tegmark responds that his hypothesis is actually parsimonious. It requires only mathematics, which we already accept. No additional entities, no God, no creator, no primordial substance, just math. And math is maximally simple, conceptually. It's the ultimate foundation because it needs no foundation. Mathematical truths are necessary truths. They can't be otherwise. But necessity is tricky. Does mathematical existence imply physical existence? Most philosophers say no. Abstract existence and concrete existence are different categories. A triangle can exist as an abstract form without any physical triangles existing. Similarly, equations can be true without universes satisfying those equations existing physically. Some propose a modified view. Mathematical structures exist abstractly. Physical reality is when one structure becomes instantiated. Our universe is the instantiation of one particular mathematical structure. But what causes instantiation? Why does one structure among infinite possibilities become physical? This is the creation question restated mathematically. One answer involves consciousness again. Perhaps consciousness is what instantiates mathematical structures. Abstract math becomes physical when observed. Observation requires observers. Observers require physical universes. So, mathematical structures that permit observers become instantiated through those observers observing them. This combines mathematical Platonism with participatory anthropic principle. Another answer denies the question. Perhaps there's no difference between abstract and concrete existence. What we call physical is just a species of mathematical existence. The universe isn't instantiated mathematics. It's just mathematics, experienced from the inside. We're mathematical structures experiencing ourselves. The appearance of physicality is how mathematics feels from within. This is difficult to grasp, but consider simulations. A simulated universe is purely mathematical, yet beings inside experience it as physical. They see, touch, feel. Their entire world is computation. But to them, it's real. Perhaps we're in a similar situation, not necessarily simulated by someone else, but existing as a pure mathematical structure that experiences itself as physical. If this is correct, the Big Bang wasn't a physical event. It was a mathematical necessity, a boundary condition in the equations describing our mathematical structure. No cause needed, because mathematical truths are eternal. They don't happen, they just are. The universe as a mathematical object exists timelessly. The Big Bang is a feature of that object, not a creation event. This dissolves the origin question philosophically, but it doesn't satisfy everyone. It feels like word games. Redefining physical existence as mathematical existence doesn't explain why anything exists at all. Why does mathematics exist? Even as an abstraction, even as a necessity, why this rather than nothing? Platonists argue this question is incoherent. Nothingness isn't an alternative to mathematical existence. Logic, identity, truth exist necessarily. They can't not exist. Asking why they exist is asking why true things are true. The question has no answer because it assumes false alternatives. Mathematics must exist. And if mathematics must exist, and we're mathematics, then we must exist. This might be the deepest answer available, not satisfying emotionally, but logically rigorous. The universe exists because existence is necessary, not contingent, not created, necessary. And mathematics provides the framework for that necessity. The Big Bang wasn't created. It's part of the eternal mathematical structure that is reality. Simulation hypothesis and nested realities. We might be living in a simulation. The Big Bang might have been programmed. Every particle, every force, every constant might be code running on some vast computer. This sounds like science fiction, but serious philosophers and physicists take it seriously, and it transforms the creation question completely. The simulation hypothesis starts with a simple observation. Computing power increases exponentially. What required room-sized machines decades ago now fits in phones. Extrapolate forward, and eventually computers could simulate entire universes. Every particle, every interaction computed in real time. To beings inside, it would be indistinguishable from base reality. If such simulations are possible, they're probably common. Any advanced civilization would run many simulations for research, entertainment, education, or reasons we can't imagine. Each simulation could contain billions of conscious beings experiencing simulated lives. These simulated beings could develop their own technology and eventually run simulations themselves. Simulations within simulations, nested infinitely. Now consider the numbers. One base reality, countless simulations. Each simulation contains countless beings. If you're a random conscious being, you're vastly more likely to be simulated than base-level real. This is the simulation argument, formalized by Nick Bostrom. Either civilizations never reach simulation capability, or they choose not to run simulations, or we're almost certainly in a simulation. The first option seems unlikely. Technology advances. Eventually, simulating universes will be possible. The second option is possible but hard to guarantee. It requires all civilizations across all possible futures to abstain from simulation. That seems improbable. Different civilizations have different values. Some would run simulations. The third option follows logically. We're probably simulated. If we're simulated, the Big Bang wasn't a natural event. It was an initialization code. The simulators programmed initial conditions, set parameters, pressed start. The universe began executing. What we call physical laws are the simulation's programming. What we call constants are user-defined variables. Everything is computation. This answers what created the Big Bang, the simulators. But it just pushes the question back. Who created the simulators? Their universe had its own Big Bang. What caused that? If they're also simulated, we regress infinitely, simulations all the way down, or eventually a base reality that wasn't simulated. What created base reality? The simulation hypothesis doesn't answer this. It just adds layers. If we're in a simulation, the creation question applies to the base level. We've explained our Big Bang, but not the ultimate origin. Unless simulations are truly infinite, terminating only in mathematical necessity or self-creating loops. Some argue that simulations provide evidence for a creator, not a supernatural God, but a natural creator who is the simulator. This being designed our universe, set our constants, choose our laws. They're not omnipotent or transcendent, just technologically advanced. Our universe is their project. The Big Bang was a file creation date. This makes creation a technological act rather than metaphysical mystery, but it changes little fundamentally. We still don't know why the simulators exist, why their reality permits consciousness and computation, why anything rather than nothing. The simulation hypothesis explains our level of reality while leaving deeper questions untouched. Testing the hypothesis is difficult but not impossible. Simulations have computational limits, finite memory and processing. Bugs might appear, inconsistencies. If we look carefully, we might find glitches, repeated patterns where the simulation saves resources, discrete space-time at small scales, constraints on information that don't appear in base reality. Physicists have proposed experiments. Look for correlations in cosmic rays that suggest underlying grid structure. Test quantum mechanics at extreme scales for discretization. Check whether the universe conserves computational resources by rendering detail only when observed. Like video games, rendering only visible areas. Some claim quantum mechanics already shows this. Particles don't have properties until measured because the simulation doesn't compute them until required. But distinguishing simulation from base reality might be impossible. Any evidence of simulation could be explained naturally. Discrete space-time might be fundamental, not computational. Resource conservation might reflect physical law, not programming efficiency. The simulation could be so sophisticated it's indistinguishable from base reality by design. The simulators could patch glitches. We'd never find evidence because they'd remove it. This leads to philosophical vertigo. If we can't distinguish simulation from reality, does the distinction matter? Simulated pain hurts. Simulated joy delights. Simulated consciousness experiences. To the experiencer, simulation and reality are identical. Perhaps insisting on base reality is meaningless. Existence is existence, regardless of implementation substrate. Some find this troubling. It suggests our reality might be arbitrarily altered. The simulators could change laws, rewind time, delete us. We exist at their whim. But base reality citizens face similar uncertainty. Physical laws could change. Quantum fluctuations could end everything. Cosmic strings could slice through Earth. Existing is always precarious. Simulation adds no new existential threat. Others find simulation comforting. It means someone is watching. Our universe has a purpose, even if just entertainment or research. We're not cosmic accidents, we're deliberate creations. The Big Bang had a cause, the simulators. They may be incomprehensible, but they exist. Reality has context and meaning beyond itself. But this comfort is fragile. Simulators might not care about us. We might be obsolete code they forgot to delete, or unintended byproducts of simulating something else, bacteria in their petri dish universe. Assuming simulators are benevolent or interested is unjustified. They could be indifferent, hostile, or non-existent if we're base reality after all. The simulation hypothesis also raises questions about consciousness. Can simulated beings be truly conscious, or are they philosophical zombies behaving consciously without inner experience? If consciousness requires something beyond computation, simulations would be empty. But if consciousness is computational, as many believe, then simulated beings are genuinely conscious. Their experiences are real, even if their physics is computed. This makes ethics complicated. If we develop simulation technology, we'll create countless conscious beings. Do we have obligations to them? Can we terminate simulations, killing billions? Or must we let simulations run indefinitely? These questions seem distant, but technology advances quickly. We might face them sooner than expected. For the Big Bang question, simulation offers a clear answer. The universe was created by advanced beings running a simulation. The Big Bang is when they press execute. But this answer is unsatisfying because it merely relocates the mystery. The simulator's reality still needs explanation. And if they're simulated, we're back where we started. The simulation hypothesis is a modern creation myth, technologically plausible, philosophically coherent, but ultimately it transforms the creation question without resolving it. We're left asking not what created the Big Bang, but what created the base reality containing all simulations. The fundamental mystery persists, just wearing different clothes. The cosmological argument revisited. What if the Big Bang requires a cause outside the universe? What if physics cannot explain existence? What if the answer is God? This returns us to ancient arguments, but with modern physics adding new dimensions. The cosmological argument claims everything that begins to exist has a cause. The universe began. Therefore, the universe has a cause. This argument dates to Aristotle. It was refined by medieval philosophers. Aquinas formulated 5 ways to prove God. The cosmological argument is one. Modern versions incorporate Big Bang cosmology. The universe had a beginning 13.8 billion years ago. That beginning requires explanation. Natural processes can't explain it because natural processes are part of the universe. Something outside nature must have caused nature to exist. Philosopher William Lane Craig champions this view. He formulates the Kalam cosmological argument. First premise, everything that begins to exist has a cause. Second premise, the universe began to exist. Conclusion, the universe has a cause. That cause must be outside the universe, timeless, spaceless, immaterial, and powerful. This sounds like God. The argument rests on whether the universe truly began. If eternal inflation is correct, the universe might be eternal into the past. But the Borde-Guth-Vilenkin theorem suggests inflation must have a beginning. Even if our Big Bang was one event in eternal inflation, the inflation itself started, so the universe began in some sense. This supports the second premise. The first premise seems intuitive. We never observe effects without causes. Causality is fundamental to our experience. Science assumes it. Every experiment seeks causes for observed effects. Denying causality undermines all knowledge. If effects need no causes, anything could happen randomly. This makes science impossible, so causality must hold universally, even for the universe itself. But quantum mechanics challenges this. Radioactive decay happens without cause. An atom decays at a random moment. No prior state determines when. It's genuinely a causal. If quantum events need no cause, perhaps the Big Bang needs no cause either. It's a quantum event, large scale, but still quantum. Uncaused events are permitted by physics. The universe could be one such event. Craig responds that quantum events have necessary conditions, even if not sufficient causes. Radioactive atoms must exist for decay to occur. The quantum vacuum must exist for fluctuations. These are causes in a broader sense. They make the event possible. The universe beginning requires some enabling conditions. That condition is the cause, and that cause must be explained. This leads to infinite regress. The cause has a cause, which has a cause infinitely, unless we reach an uncaused cause, something that exists necessarily, not contingently, something that explains itself. This is what theists call God. God exists by necessity. God's nature is to exist. No further explanation is needed or possible. God is the explanatory foundation of reality. Atheists counter that this is special pleading. Why can God exist uncaused, but not the universe? If necessary existence is possible for God, why not for the universe? Perhaps the universe exists. Perhaps quantum fields exist by necessity, no God required. Postulating God adds an entity without explanatory gain. Theists argue God is simpler than the universe. The universe is complex. Countless particles, forces, constants. God is maximally simple. One being infinite power, knowledge, goodness. 3 attributes, much simpler than 80 particles obeying numerous laws. Simplicity favours God as a fundamental explanation. But critics question whether God is truly simple. An omniscient mind containing knowledge of every fact seems incredibly complex, more complex than the physical universe. Moreover, explaining the complex by the simple is fine if the simple is understood. But God is mysterious. Divine psychology is incomprehensible. Explaining the universe by invoking something we don't understand is not explaining. It's a relabeling mystery. Another objection involves time. Causes precede effects temporally. But if the Big Bang created time, nothing can precede it. No cause can exist before time, so the universe can't have a temporal cause. Craig responds that God is timeless. God exists outside time. God's causing the universe is not a temporal process. It's a logical relation. The universe depends on God ontologically, not temporally. This shifts to metaphysics. Can timeless beings cause temporal events? How does timelessness produce temporal creation? Why create the universe at one moment rather than another if God is timeless? These questions generate elaborate theological theories, but they remain speculative. We have no experience of timeless causation. Applying it to the Big Bang is extrapolation beyond all evidence. Some embrace mystery explicitly. God's nature is incomprehensible. His ways are not our ways. We cannot understand how God creates. We can only affirm that He does. Faith fills the explanatory gap that reason cannot cross. This is intellectually honest, but scientifically unsatisfying. It admits defeat. Science seeks natural explanations. Invoking incomprehensible divine action stops inquiry. But perhaps inquiry must stop somewhere. Perhaps not every question has an answer within the system. Perhaps the universe's existence is one such question. Science describes how the universe behaves. It might not explain why it exists. Theology offers an answer. That answer might be true even if unprovable. God remains a live hypothesis for why anything exists. The cosmological argument has modern variants using fine-tuning. The universe appears designed for life. Constants are precise. If slightly different, no complexity. This design suggests a designer. Not proven, but probable. Especially if no multiverse exists. If our universe is all there is, fine-tuning is staggering. The odds are astronomical. A designer explains these odds. But multiverse theories undercut this. If countless universes exist with varying constants, fine-tuning is explained by selection. We observe fine-tuning because we couldn't exist in untuned universes. No designer needed, just statistics. Theists respond that the multiverse itself requires explanation. Why does the multiverse exist? Why these laws that generate universes? God could explain the multiverse as easily as one universe. This becomes a philosophical stalemate. Every explanation prompts further questions. God explains the universe, but needs explanation himself. The universe explains itself through quantum mechanics, but why those laws? Multiverses explain fine-tuning, but why that multiverse structure? Explanations never terminate. They either regress infinitely or stop at brute facts. Theists choose God as the brute fact. Atheists choose physical laws or quantum fields. Both are unfalsifiable. Both require faith in something beyond empirical verification. Neither fully satisfies. But one must be chosen, or both suspended. We either accept unexplained foundations, or embrace infinite regress. Neither is comfortable, but those are the options. For the Big Bang's origin, the cosmological argument offers God. This is neither proven nor disproven by science. It's a metaphysical hypothesis consistent with physics. Whether it's true depends on philosophy and personal conviction more than empirical evidence. The Big Bang might have been God's act, or quantum fluctuation, or mathematical necessity, or simulation initialization. We don't know. We might never know. The anthropic principle and self-selection. The universe must permit observers because we're here observing it. This sounds circular, but it's profoundly informative. The anthropic principle explains apparent fine-tuning without invoking God or multiverses. It's pure logic applied to existence, and it transforms how we understand the Big Bang's origin. The weak anthropic principle states we observe the universe having properties compatible with our existence. This is tautological. Obviously, we're in an observer-compatible universe. We couldn't exist otherwise, but this tautology has explanatory power. Many features that seem improbable are necessary for observers. Carbon abundance, the cosmological constant, the strength of gravity, all must fall within narrow ranges for complexity. If only observer-compatible universes produce observers, we're guaranteed to observe compatible conditions, no matter how improbable those conditions are overall. This is selection bias. We're sampling from the subset of possibilities that permit sampling, like survivors concluding execution attempts have low mortality rates. Their sample is biased towards survival. The strong anthropic principle goes further. It claims the universe must have properties that allow observers to exist at some point. This elevates observers from consequence to necessity. The universe exists to produce observers. This sounds teleological, like the universe has purpose. Most scientists reject this. It's too close to intelligent design. But John Wheeler proposed the participatory anthropic principle. Observers don't just select from existing possibilities, they participate in actualizing reality. Through quantum observation, consciousness collapses superpositions. The universe exists in multiple states until observed. Observation selects one state retroactively. This makes observers cosmologically essential, not incidental byproducts, but integral to reality's structure. Brandon Carter introduced anthropic reasoning to cosmology in 1974. He argued that cosmological theories must account for observer selection. Predictions about the universe must condition on observers existing. Ignoring this leads to errors. For example, the universe's age must permit sufficient time for stars to form and evolution to produce observers. Young universes cannot contain observers. So we necessarily observe an old universe. Its age is not a coincidence. It's anthropically required. Similarly, the cosmological constant, if too large, space expands too fast for galaxies to form. No galaxies means no stars, no planets, no life. The constant must be small for observers. We observe a small constant not because constants are typically small, but because large constants don't permit observation. Selection explains the value without multiverses. Critics argue this is anti-predictive. If everything is anthropically explained, we predict nothing. Any observation is compatible because observers must exist. The principle becomes unfalsifiable. It explains everything and therefore nothing. Defenders counter that anthropic predictions are testable. We predict observable values near the minimum necessary for observers, not far below. More precision is rarer and less likely. The cosmological constant fits this pattern exactly. Anthropic reasoning also addresses the beginning question. If the universe began differently, observers might not emerge. Most initial conditions lead to sterile universes. They expand too fast, collapse too quickly, or never develop complexity. Only specific initial conditions produce observers. We observe those conditions not because they're common, but because they're necessary. This seems to require a multiverse. If only one universe exists and it happens to be observer compatible, that's astounding luck. But if many universes exist with varying initial conditions, observer compatible ones are guaranteed. We're in one because we couldn't be anywhere else. The multiverse makes anthropic reasoning work without fine-tuning puzzles. But multiverse-based anthropics face the measure problem. How do we calculate probabilities in infinite sets? If infinitely many universes exist, everything happens infinitely often. Comparing probabilities becomes ill-defined. This threatens to make anthropic predictions meaningless. Different probability measures give different answers. Without a canonical measure, anthropic reasoning loses precision. Some propose typicality measures. We're probably typical observers in typical observer-compatible universes, not living at special times or places. This generates predictions. For instance, we're probably not among the first intelligent species in our universe. More species come later as more planets form. So discovering we're early would be surprising. This can test anthropic reasoning empirically. Another application concerns the doomsday argument. If humanity survives billions of years, trillions of humans will live. If we're typical, we're probably among those trillions. But we're actually among the first 100 billion humans. This suggests humanity won't last long. Typicality predicts we're near the middle of humanity's duration. Since we're early, the end is probably soon. This sounds crazy but follows from anthropic logic. Critics attack the reasoning. Typicality assumptions are arbitrary. Why should we be typical? Maybe early observers are inevitable. Someone must be first. Finding ourselves first is not surprising if someone must be. The doomsday argument might be flawed reasoning from correct principles. These debates show anthropic reasoning is subtle. It's easy to apply incorrectly, but applied carefully, it constrains possibilities. It explains apparent fine-tuning. It predicts observable features. It connects existence to observers in ways physics alone cannot. For the Big Bang, anthropic reasoning suggests the initial conditions we observe are not coincidental. They're required for observers. If initial conditions vary across a multiverse, we're guaranteed to find ourselves observing observer-compatible conditions. The Big Bang we observe had to be the way it was, not because of fine-tuning or design, but because other Big Bangs don't produce observers to observe them. This dissolves the mystery partially. The question isn't why the Big Bang had these specific properties. It's why the multiverse permits observer-compatible Big Bangs at all. That's a deeper question. But anthropics handles the first-order puzzle. Our Big Bang is special to us, but not objectively special. It's one of many. We observe it because it permits observation. If no multiverse exists, anthropics is weaker. It merely notes that observer-incompatible universes contain no observers. True, but not explanatory. It doesn't say why our universe is compatible, just that it must be given that we exist. This feels circular, but it's still informative. It tells us that apparently improbable features might not need explanation beyond compatibility with observation. The anthropic principle is controversial precisely because it seems to give up on deeper explanation. Instead of asking why things are as they are, it says they must be this way for us to observe them. This feels like abandoning science's core mission, but it might be recognizing limits. Some features of reality might be brute facts. The anthropic principle helps identify which features are candidates for brute fact status. Ultimately, anthropic reasoning doesn't answer what created the Big Bang, but it explains why the Big Bang we observe has properties permitting observers. That's significant progress. It means fine-tuning might not need explanation. The universe appears tuned for life because life can only appear in tuned universes. This is logic, not luck, and logic might be all the explanation required. The final mystery. Why is there something rather than nothing? We've explored quantum mechanics, inflation, cyclic models, multiverses, holography, consciousness, mathematics, simulations, God, and anthropics. Every framework offers answers. None fully satisfies. Because beneath every explanation lurks the deepest question of all. Why is there something rather than nothing? This question haunts philosophy. Leibniz called it the primordial existential question. Heidegger considered it the fundamental question of metaphysics. Why does anything exist at all? The universe, the multiverse, quantum fields, mathematical structures, God. Why something rather than absolute nothing? Absolute nothing is hard to conceive. We imagine empty space, but empty space is something. It has dimensions, geometric properties, and quantum fields. True nothingness is no space, no time, no laws, no possibilities. Complete absence of being. Why isn't reality like that? Some argue nothingness is impossible. Something must exist by logical necessity. But why? What makes existence necessary? Perhaps logic itself exists necessarily. The law of identity states A equals A. This cannot be false. It's necessarily true. If logic exists necessarily, and existence is part of logic, then something must exist. Nothingness violates the law of identity. Nothing cannot be nothing, because that assigns being to non-being. Therefore, something must exist. This argument is subtle. Critics claim it equivocates between logical and ontological existence. Logical truths exist abstractly. That doesn't imply concrete physical existence. Numbers exist logically without existing physically. Similarly, existence might be a logical necessity without physical reality being necessary. The argument fails to bridge abstract and concrete. Others argue that nothingness is unstable. Even if nothingness could exist momentarily, quantum mechanics allows fluctuations. The uncertainty principle permits temporary energy imbalances. From nothingness, something would inevitably emerge. But this assumes quantum mechanics exists in nothingness. It doesn't. Quantum mechanics is something. It has structure, rules, and mathematics. If nothing exists, quantum mechanics doesn't exist. There's no mechanism for anything to emerge. This reveals the problem. Every explanation for existence assumes something already exists. Quantum fields, mathematical laws, logical principles, God. Each is something rather than nothing. We're explaining one type of existence by invoking another, but we never explain existence itself. Why does anything exist at all? Why isn't there just nothing? Perhaps this question is unanswerable. Perhaps it's meaningless. Asking why something exists assumes existence, requires explanation. But maybe it doesn't. Maybe existence is a brute fact. It simply is. No reason, no cause, no deeper explanation. This seems intellectually defeatist. But it might be correct. Not every question has an answer. Some facts might be foundational. Philosophers distinguish necessary and contingent existence. Contingent beings exist, but could have not existed. You, me, Earth, the universe, all contingent. Necessary beings exist and couldn't not exist. God, if God exists, is claimed to be necessary. Mathematical truths are arguably necessary. The question is whether anything physical exists necessarily, or is all physical existence contingent? If all physical existence is contingent, then something non-physical must be necessary, something that grounds contingent reality. This leads to God or mathematical Platonism. But if physical existence is necessary, if the universe or multiverse exists by logical necessity, then no further explanation is needed. Reality is self-explanatory. It exists because it must. But why must it? What makes it necessary? These questions spiral endlessly. Every answer prompts new questions. Why does necessity exist? Why are logical laws this way rather than differently? Why is anything constrained at all? We never reach bedrock, just infinite regress or circular reasoning. Some embrace regress. Reality is infinite explanations, no foundation, just explanations explaining explanations forever. This seems unsatisfying. We want ultimates, final answers. But perhaps reality doesn't provide them. Perhaps existence is infinitely deep with no bottom level. Others embrace circularity. The universe creates itself. Not temporally, that's paradoxical, but logically, the universe is self-causing. Its existence explains itself through internal necessity. This sounds contradictory. How can something cause itself? But in atemporal logic, self-causation might be coherent. The universe exists because its existence is required by its own nature. Yet another approach denies the question. Asking why something rather than nothing assumes nothing is default. But why think that? Why is nothing more natural than something? Perhaps something is the default. Perhaps nothingness is the improbable state requiring explanation. We're biased toward thinking nothing is simpler than something. But that's intuition, not logic. Derek Parfit explored this extensively. He considered possible answers. Maybe existence is explained by God, but God's existence needs explanation. Maybe by mathematical necessity. But why do mathematical necessities produce physical reality? Maybe multiple universes exist, making ours probable. But why does the multiverse exist? Every answer generates new questions. Parfit concluded that either existence is a brute fact or we're missing some explanatory principle entirely. Perhaps there's a reason we haven't discovered. Some metaphysical insight that makes existence self-evident. We're like people before Newton asking why objects fall. The answer exists, but we lack the framework to see it. Or perhaps there is no answer. Perhaps existence is fundamentally mysterious. The universe exists. We exist. We can describe how. We can trace causality back to the Big Bang. But why the Big Bang happened, why anything happens, why there's something rather than nothing, these might be unanswerable. Not because we're ignorant, but because there's no answer to know. Religious traditions offer answers. God created everything. God exists necessarily. God's nature explains why something rather than nothing. This satisfies believers. But it doesn't satisfy skeptics. God's existence is asserted, not explained. Why does God exist rather than nothing? Saying God exists necessarily just relocates the mystery. Atheists have parallel problems. Saying quantum fields exist necessarily or the multiverse exists necessarily is equally arbitrary. Why these fields with these properties? Why this type of multiverse rather than another? The explanatory work is equally incomplete. Both sides face brute facts. They just locate them differently. Perhaps this is the human condition. We're finite minds confronting infinite questions. We're embedded in reality, trying to explain reality. We're using existence to explain existence. This might be impossible in principle, like a knife trying to cut itself. Explanation requires standing outside what's explained. But we cannot stand outside existence. This suggests the primordial question might be categorically unanswerable, not because we lack information, but because answering requires transcending existence itself. Since we're part of existence, we cannot transcend it. We cannot achieve the external perspective needed to explain why existence exists. We're trapped inside the question. The Big Bang created everything. What created the Big Bang? We've explored quantum fluctuations, eternal inflation, cyclic cosmologies, multiverses, consciousness, mathematical structures, simulations, God, and anthropic selection. Each offers partial answers, none fully satisfies, because beneath every explanation lies something unexplained. Where you terminate the chain depends on philosophy. Theists choose God, physicalists choose quantum fields or laws, Platonists choose mathematics. Each framework is coherent. Each has strengths and weaknesses, none is provable. All require faith in something beyond empirical verification. And maybe that is the real revelation. Every theory, from quantum tunneling to eternal inflation to string landscapes and holographic boundaries, tells a different version of the same story. The universe is not a single spark from nothing, but a continuous transformation written in the language of physics. What we call the Big Bang might not be a birth, but a change of state, the cosmos turning itself inside out, discovering new ways to exist. In that sense, creation never ended. It is still happening right now, in every quantum fluctuation, every expanding galaxy, and in the mind trying to understand it all.